Hello everyone, I'll be discussing the UNet transformer, which is basically another architecture similar to SHRED. So for the architecture abstraction, we have a UNet slash CNN or convolutional neural network decoder, and we have a basic encoder for transformer networks. As you can see, there's a normalization layer which basically speeds up training. You can also see that we have multi-headed attention. We also have positional encoding to determine relative position of time series data, for instance, and so on and so forth. So I'll explain each class in depth. So we have the UNet decoder class here, which basically has several components. We have the convolutional transpose, one-dimensional transpose, and we also have the convolutional one-dimensional layer, max pooling, and such. However, in this example, we only used a simple convolutional neural network, and we started with 3 channels, and we increased to about 2048, and we made sure to maintain the length of the sequence, which is why we altered the kernel size between 2 and 4, and so forth. As you can see, our activation function is a ReLU network, and so we prefer to keep it as that, and increasing the channels to around 2048 really helped the performance of our model. It could have also been altered, however, via hyperparameter tuning, we believe 2048 was very good. So the positional encoder class. So this is basically a standard positional encoder for a transformer network. We didn't really change much. In this, as I previously stated, the positional encoder would be helpful for determining relative position of time series data or sequences. The div term, for instance, in this allows the model to learn relative position more easily. The D model is the embedding dimension, and the goal is to learn temporal relationships. So now we have the time series U-transformer class. The time series U-transformer class combines all the former classes. So it basically combines the UNet decoder as well as the positional encoder, and we also have the transformer encoder layer, which I can discuss a little bit more. For example, multi-headed attention is very helpful for determining, for learning more regarding temporal relationships, such as what is it doing, so on and so forth. And so this is currently what it looks like. We have a dimension feed forward of 128, and the activation function is the GLU for the transformer encoder layer. And we used a GRU, which allowed for faster training, which is part of the reason why we used it. We made sure not to have too many layers, so we capped it at 2, and we used an input size of 3, which is the same dimension, which is the same as our D model. As you can see here, this is currently what the forward function looks like. It uses a mask as normal, and applies the positional encoder. So as to discuss the performance of SHRED and the U-transformer, so the U-transformer utilizes the transformer architecture, but it takes longer to train than SHRED. The reconstruction root mean squared error for the U-transformer is about 0.20. The reconstruction root mean squared error for SHRED is about 0.17. And so both models perform well. And as you can see here, the difference between SHRED and the U-transformer is that they both have different parameters. The U-transformer appears to do better with more data. And as you can see this picture here on the bottom right, you can see that we're comparing it between the base line as well as the ground truth, and you can see they're almost indistinguishable, so to speak, as well. And for more emphasis, we only train these on 20 epochs. Now, if you look at the latent space, we have on the left side how the latent space is changing periodically, and on the right side how it's changing linearly. And you can see on the left that that we capped it at about 160 to 200 minutes. to see how it might be changing along at that time, to see periodically. And on the right, we notice that as the model continues to, or as time progresses, certain the latent space features start to become more pronounced. So that's something else to keep in mind. And we also used a lag of about 52 seconds. So to keep that in mind as well. Or in other words, a time delay of about 52 seconds per measurement. So future directions, your transformer remarks. So what we might do in the future would be to provide the model with more data, maybe add additional sensors, utilize a custom loss function, maybe customize the optimizer, or alter the default activation function. And so those are all things we might do in the future. Thank you.